Welcome to Module F, Lecture 10. In this lecture, we shall discuss and rather we will continue our discussion about stochastic traffic assignment, and also before we close, we shall give you a brief introduction to dynamic traffic assignment technique. In lecture 9, the last lecture we discussed about stochastic traffic assignment, why we need to consider the stochasticity, the perception error, the variability due to the perception, the variability in the perceived travel time or travel cost, and then use of multiple path because of this perceived variability in the perceived travel time. So, then we talked about the pure stochastic assignment, also took the example problem and solved that using the Dial's algorithm, the forward pass and then the backward pass. So, with an example we have explained. So, now you know what is stochastic traffic assignment, why we go for it, and what is pure stochastic traffic assignment. So, in continuation to that, we shall discuss in this class or lecture about stochastic user equilibrium. So, we say stochastic assignment, we discussed pure stochastic assignment, and in this lecture we shall discuss about stochastic user equilibrium, SUE. Now, pure stochastic assignment considers spread of routes based on variability in the perceived route cost or the path cost or the route travel time or path travel times. So, we know that true travel time is not known, information availability is limited. So, the available information not 100% information is available to everybody, and the true travel time is not known. So, we take route individual, we take route based on our perceived travel time. So, pure stochastic assignment considered the spread of route to account for this variability in the perceived travel time. In case of pure user optimized equilibrium traffic assignment or equilibrium traffic assignment model, this variability happens because of the capacity restraint effect. We said that if we do not consider stochasticity, that is also, but consider a realistic situation, consider a typical urban condition, urban transport condition. Nearly every big city you have demand and supply, there is great imbalance. On many links or many segments, the demand may be even more than the available capacity during certain hours of the day. And even when the demand is less than the capacity, then also the demand is very significant. So, there will be congestion effect, and because of that the travel time will no more be the shortest path, will no more be the shortest path once the flow or the demand is assigned, and alternative paths will be used. So, in pure user optimal equilibrium UE, okay, in pure user optimal equilibrium, multiple paths are chosen because of the capacity consideration, because of the congestion consideration. However, and so what is really happening, that in pure user optimal equilibrium, multiple paths are taken because of the capacity consideration, because of the congestion consideration, and in pure stochastic assignment, multiple paths are taken because of the variability in the perceived travel time or travel cost. Now, what is bit more realistic is to consider both these aspects. So, in reality if we consider a practical situation, this stochasticity also will be there, because people will not have, all users will not have the true information about the travel time. So, there will be variability and everybody will actually try to optimize his or her perceived travel time rather than the actual travel time. That is also true, but the other end is also true that roads will have capacity limitation, demand may be more than the capacity, or even when it is not more than the capacity, then also there will be significant congestion effect, and therefore, because of that also multiple paths will be chosen. So, reality is a mixture of these two, stochasticity or the variability in the perceived travel time, and also the capacity constraint or capacity restraints and congestion effect. So, when we try to consider both aspects together, then the kind of equilibrium what we are seeing is stochastic user equilibrium. So, not just stochastic assignment, not just deterministic user equilibrium DUE, but it is stochastic user equilibrium. So, stochasticity is also considered, capacity restraint is also considered, both are considered. So, the equilibrium is achieved here with this kind of assumptions or reality. Each user chooses the route with the minimum perceived travel cost. Remember that we are sticking to perceived travel cost. So, the variability is there, stochasticity is there. So, each user chooses the route with the minimum perceived travel cost. In other words, under stochastic user equilibrium, slight deviation from the deterministic user equilibrium. Carefully note this, no user has a route with lower perceived cost, and therefore, all stay with their current routes. In DUE, deterministic user equilibrium, perfect knowledge, no variability in the perceived cost. So, all the routes will have equal travel time, and we said any unused route will have either equal or higher travel time. That was the assumption. Here we are deviating, because we are everything is going around perceived travel time or perceived travel cost. So, we are saying we are still reaching to an equilibrium where no user has a route with lower perceived cost. So, nobody is interested to change route from one route to another route, simply because no individual is able to bring down the perceived cost by changing route. Everybody is not thinking still the same time, that variability exists, but whatever I think, whatever you think, whatever every other individual is thinking, their perceived travel times may be different for different paths, but everybody is thinking that if I change route individually, I cannot bring down my perceived travel time further. So, with variability in that perceived travel time, still we are reaching to an equilibrium. So, this equilibrium is going to be different than the deterministic user equilibrium, and because the perceived travel times and travel cost along different paths are different to different individuals. So, all the routes still will not have equal cost or equal time. So, I to j, maybe there are 4 alternative paths, but all paths still may not give me and will not give me rather equal travel time. So, it is not going to be like deterministic user equilibrium, but still that equilibrium will reach. Why? Because everybody will feel like I cannot reduce my perceived travel time further by changing the route, and every individual will feel like that. So, that is the equilibrium. What is equilibrium here? When nobody is interested to change the path further, that is our equilibrium. So, the equilibrium will be when no one is changing the route further. The flow is not changing further, but the travel time on all the alternative paths still may not be same. So, the difference between stochastic and Wadroff's user equilibrium, as I said, is that in SUV model each driver defined travel costs individually. Please carefully note this word individually, instead of using a single definition of cost and value applicable to all drivers. So, in SUV assignment is obtained by applying the equilibrium approach to congested networks under the assumption of probabilistic route choice behavior. Stochasticity is there. So, the model is a probabilistic model. So, route choice behavior is a probabilistic, like the mode choice behavior, probabilistic mode choice model. Similarly, here also it will be probabilistic route choice model, but then still the equilibrium will reach. Equilibrium will reach in a slightly different manner, as I explained. At SUV, no motorist can improve, again I am repeating, his or her perceived travel time. No one can improve or reduce, in this case, his or her perceived travel time by unilaterally changing routes. So, this follows directly from the interpretation of the choice probability as the probability that the perceived travel time on the routes is the smallest on all routes connecting to the OD under consideration. Please carefully observe this statement. What we are saying, this follows directly from the interpretation of the choice probability as the probability that the perceived travel time on the chosen route is the smallest of all the routes connecting the OD under consideration. So, that is where the stochastic user equilibrium is reached. The UV condition are a particular case of SUV. Why I said so? Very simple. Why SUV? SUV is because of the variability, that is what is the difference. So, if you consider there is no variability or the variability is 0, that boils down to UV or DUV, deterministic user equilibrium. Generally, I am speaking UV. Okay? So, when stochasticity and without stochasticity. So, without stochasticity is a specific case of stochasticity when the variability is 0. So, the UV condition are a particular case of SUV when the variance or variation of travel time perception is 0. The SUV conditions are identical to the UV condition. You may call it UV, you may call it with capacity consideration or capacity restraint consideration, you can call it as DUV. Now, how to go ahead with this? So, we initialize, do the initialization, perform a stochastic network loading as we have discussed in lecture 9, previous lecture only, based on a set of initial travel time. We know the initial travel time, 0 flow travel time is known, and this generates a set of link flow x a 1 set n equal to 1, n is the number of iterations. Then what we are doing? We now know that how much flow has been assigned initially in the initialization part. So, based on that, what is the travel time? With that flow, we update then the travel time. Then we go for direction finding. Direction finding means in this case perform a stochastic network loading procedure based on the current set of link travel time. So, we try to reassign with the current flow we reassign, but then this will yield what? This will yield an auxiliary link flow pattern. Do you remember this auxiliary link flow? We discussed earlier in the context of deterministic user equilibrium assignment under method of successive average, yes, that MSA technique. So, we are exactly now we initially do a stochastic network loading and then we further update the flow, do again a stochastic network loading, but then whatever we are going to get, we get that as auxiliary flow, auxiliary link flow pattern, exactly like the MSA, what you have already studied, you already know. We discussed all this with an example also. So, this auxiliary flow we shall get. Then we have to update. You remember that we every time we update the link cost, we assign the flow again, and there we did deterministic assignment. So, that means whatever is the shortest path, along the new shortest path we loaded. Entire flow was loaded along the shortest path to get the auxiliary link flow pattern. But here the only difference is we shall again do a stochastic network loading. So, not everything will be loaded along the shortest path, but all paths will get their share as per the travel time and the link cost function based on the current loading. That is the only difference, but otherwise this method of successive average is absolutely similar, no difference. Only the auxiliary flow, how we got there, we did deterministic assignment. So, we with the current loading we got the revised travel time, and accordingly based on this revised travel time we then again assigned the flow, but the complete flow was assigned along the shortest path. And multiple times we did that. We updated the link flow and again started calculating, recalculating the travel time and accordingly load the network. But every time we are loading using along the shortest path, what is current shortest path, just assign every flow there. But in this case, when you are using MSA under SUE, stochastic user equilibrium, then every time the assignment is done, this is stochastic network loading. So, stochastic assignment is done, that is the only difference. The remaining is simple as it was stated earlier. You get the auxiliary flow, then you remember this equation. Now, we actually update the link flow, that was the auxiliary flow. Actual link flow, how we update? X n plus 1 equal to x a n plus 1 equal to x a n, whatever was the previous flow, plus 1 by n into within bracket y n minus x a n. What is x a n? X a n the previous whatever was the flow, and y a n is what? Y a n is the auxiliary flow, what you have got in the nth iteration. So, accordingly we update the link flows for n plus 1th iteration. And then in this case, what is the convergence criteria? Earlier when we applied this MSA, what was our convergence criteria? Convergence criteria was when the travel time on alternative paths are same. Here No, here we do not use travel time, because still travel time variations will be there, because it is stochastic assignment fundamentally. So, what we do? We see when iteration to iteration the flow along the alternative paths are not changing significantly. So, you set a limit what is acceptable error, and when the change in path flow is less than that, maximum change in the path flow is less than your permissible limit, then you say I have reached to an equilibrium condition, and that is the answer. And again, under that condition also the travel time on all alternative paths are not going to be same, because it is stochastic assignment. So, take an example here. There are two links, link 1, link 2, the travel time functions are given, T 1 equal to 1.25 plus 1.25 within bracket 1 plus x 1 by 100 800 to the power 4, just like BPR function, right. So, link 2 also the travel time function is given. We are saying that 4000 unit flows are to be distributed on link 1 and link 2, and this is the logit formula that may be applied, 1 by 1 plus into the power theta into T 1 minus T 2, and then when you apply MSA and show the results for intermediate thing, we are assuming that theta value is 1 minute to the power minus 1. So, initialize what we know, the 0 flow travel time 1.25 and 2.5. So, accordingly you do the stochastic loading and you find that x 1 is 3109, x 2 is 891. Then with 3109 as x 1 and 891 as x 2, we calculate revised travel time T 1 and T 2 for iteration 1, and using this given link cost function, and you find out T 1 is 286 and T 2 is 3.26. So, the stochastic loading again is done. Obviously, the auxiliary load auxiliary flow will go to all T 2, that is what is done. So, y 1 is 0 in this iteration and y 2 is 4000, because T 1 and T 2 is like this. Then new flow pattern you calculate exactly using the same formula as I said, x a n plus 1 for n plus 1th iteration, what will be the actual flow we are updating, that is equal to what was the flow in the nth iteration plus a change. What is that change? That change is 1 by n within bracket what is y n a auxiliary flow in nth iteration for that link or that path, minus what was the actual link flow in nth iteration. So, here you do exactly the same manner. So, you calculate x 1 as 0, x 2 as 4000. Now, no convergence. So, change is very significant. Obviously, the first iteration there will be a big change, and then you set n equal to n plus 1, go to step 1, that means again recalculate the travel time and then again do the stochastic loading, and this time it will not be 0 and 4000, 0 and 4000 because of the so huge difference in the travel time. So, it will not be again 0, both will get some flow, that is the auxiliary flow, and again we will come back and update the flow for the n plus 1th iteration. Like that we will keep on doing, and when we find the maximum change in flow from n and n plus 1th iteration is less than the error level, acceptable error level, or no significant change in the flow from one iteration to another iteration, then we stop. So, let me now show you the table, a very similar one. So, we start with 0th iteration 1.25 and 2.25. So, you get the auxiliary flow, link flow, and then as you proceed, the link travel times are calculated based on the updated flow what you get in the last two columns, link 1 and link 2. Accordingly, the next row or next iteration travel times are calculated, auxiliary flow are assigned, okay. And as you can see, initially maybe something is 0, but as you proceed, finally auxiliary flows you are doing actually stochastic loading. So, both links are getting some values and you are doing the update, and finally you stop. And then if I want to, just for example, if I want to show how the link flow has varied across different iterations, you can see here x axis shows the number of iteration and y show flow in link 1. So, initially the fluctuations are high, and then slowly the fluctuation becomes smaller and smaller and the value gets stabilized. So, that means iteration to iteration the change is not so significant. So, you can say that the flow has stabilized or the equilibrium has reached. But even in this case, the travel time on alternative paths will not be same, as you can see here. So, that is the difference between the change in the flow got minimized and minimum value it has reached. So, no significant change in flow iteration to iteration, right, that we have achieved, but the travel time will still be different. So, that is what it is. So, the convergence of MS algorithm and SUA problem is rather slow for the congested network, and for very congested network it is found that the user optimal equilibrium provides a good approximation to stochastic user of equilibrium, and the convergence is faster. So, in mildly congested network, the variation in the perceived cost can be expected to be more significant as compared to the actual cost in heavily congested network. So, this suggests that generally, this is from experience it is found that this suggests that use of SUV would be advantageous in low to medium congested assignment problem, right. So, if the network is heavily congested, then the difference may not be that significant. So, for very congested network, UA provides a good approximation of SUV. So, we have almost come to the end. So, the static assignment models, all boxes are green now. What is remaining is the dynamic assignment model. So, a few minutes we shall spend now on dynamic assignment model before we close this lecture. Now, static assignment model proves to be ineffective when transient state or transient system behavior needs to be evaluated. For example, creation, propagation and dissipation of queues in the process of congestion or in the context of congestion building. Then demand peaks in rush hours and temporary reduction in link capacity, or effect of real time control or user information strategies. Transient stage, that means what I am trying to mean when time enters as a variable. All what we said for a reasonable period of time, when the demand is not changing, network is not changing, nothing is really changing, state remains same over that period of time, then what is really happening during that period? But in reality what happens? Everything is also a function. So, time is another dimension. You go to a network in the morning 8 o'clock, it may be not much traffic, but then traffic builds up, peak hour is approaching, peak period is approaching, then again peak period goes slightly going down. So, the whole process is function of time, demand varies over time. So, in that process, so one is that it is a function of time, and what you do at time t will impact the network state at time t plus delta t. So, how the traffic has been distributed at time t will have an impact on the state of this alternative paths at time t plus delta t. So, t plus delta t decision will also depend based on that whatever is the demand at t plus delta t time, what happened at t time, what was the demand, and then how the route choice happens and all that. So, the time enters as another important consideration. So, everything is now time dependent. That means, whatever assignment we all did, we applied it only one time. Now, the one time assignment will not work. So, repeatedly we have to do it over a period of time, update and then proceed further. So, dynamic traffic assignment are able to reproduce dynamics within the reference period. So, if we say 8 to 12, the dynamics, the demand is not going to be same from 8 to 12 in the starting from 8 a.m. to 12 noon. So, DTA are able to reproduce dynamics within the reference period of the system in question, simulate the system's inner working and reproduce its evolution in time. Time is a very, very important thing. So, everything now becomes a function of time. So, we said it's maybe if always it is like this, then how things are going to happen. Then deterministic static assignment techniques are all fine, nothing was wrong. But then in reality some more we are trying to be more and more realistic. So, if you consider a more realistic situation, if you want to consider, then you have to consider the dynamics and you have to accept that it is a function of time. So, dynamic traffic assignment models or models within day dynamics are recently developed. That is where we stop here. So, the all still now it is evolving. Given their capacity, why they are so important these days or in the modern era of traffic assignment and traffic control? Because given their capacity to reproduce dynamics within the reference period of the system in question. The common feature of these models is that they depart from the standard static assignment. As I said earlier, those assumptions should deal with time variant or time varying flows. As I said, it is building up 8 o'clock something, 8:15 something, 8:30 something. The demand is also not same. Demand is also changing over time. So, how the decisions are, the way the decisions have been made at time t, what is the state, that will also impact the traffic state at t plus delta t, and therefore, also will influence the decision making at t plus delta t. Okay? So, these models may be deterministic or stochastic. That again, now you consider this is the third dimension. So, if you this is the time function. So, three aspects, initially we say perfect knowledge, no perception error, deterministic, no capacity constraint part and no variation over time, demand variation over time. Then we say deterministic and stochastic. One considered the change in the perception, the error in the perception, because nobody has got the perfect knowledge, it is all perceived time, perceived cost, perceived route characteristics. So, the stochasticity comes into picture, capacity constraint then come into picture, and we ended earlier when we discussed about our stochastic dynamic a stochastic user equilibrium, that we are considering stochasticity and considering also the capacity constraint. Now, this is a new dimension, function of time. Demand itself is function of time. So, everything whatever we have done, we cannot do one time, but things are happening again and again. Every time, every delta t time, the decision makings are happening. Now, once you call dynamic, you are actually focusing then on the time dynamics, time variant flow. Then assignment, okay, you have options, you can consider it deterministic assignment, you can consider inside against static stochastic assignment, whatever will be your assumption, you can do both. Now, dynamic process models for within day dynamics system can be expanded to include, also we can expand to include real time information by using advanced traveler information system, what is popularly known as ATIS, and also advanced traffic management system, ATMS. Real time, if you provide information, predictive information, en route information, what type of, every type of information will have different impact. What it normally used to be based on historical experience, that is one type of information. Predictive, it is another type of information. I am only giving the instantaneous traffic information, that is again one type. So, which way you display information, qualitatively, quantitatively, so many things, everything will have an impact. So, as I say, TIS is more awareness of the network conditions by providing potential traveler with information of the network's current performance, both en route and pre-route. And similarly, ATMS for providing the productivity and efficiency of the traffic networks under recurrent and non-recurrent congestion both. What is recurrent congestion? Every day the traffic is volume is high, so congestion occurs, that is recurrent, every day is happening. What is non-recurrent? Suddenly one vehicle breakdown has come. So, suddenly this congestion happens. It does not happen, not that that location every day there is a vehicle breakdown, but recurrent congestion happens every day, or maybe a traffic accident, two vehicles met with an accident and therefore, the congestion occurs, non-recurrent, does not happen every day at that location at that time. Both can be considered. So, depending on what you are doing, how you are assigning, you can then have, it is not user optimal alone, but we can say dynamic user optimal, because we are doing user optimal, but also considering the time dynamics, time variant flow, or you can be dynamic system equilibrium, or also you can have dynamic stochastic user optimal equilibrium. What you say that SUO, stochastic user optimal, or SUE we say, it is all the same, equilibrium or optimal. Okay. So, here in this case one more term will get added. I am also considering the time dynamics. So, it is not only stochastic user equilibrium or stochastic user optimal, but it is dynamic stochastic user optimal. Now, based on the level of detail with the representation of traffic, network loading models are typically classified as macroscopic, mesoscopic and microscopic. You can understand by the terminology, we cannot go into further details, because we have the limitations of time and number of lectures that we can schedule. So, macroscopic is at macro level, microscopic you know each vehicle to vehicle level, most detail level, and mesoscopic is somewhere in between. All different models are available and different platforms are also available. So, with this I would say that now you look at this flow chart, all are green, all boxes. So, we tried to give you an overall understanding of various approaches to traffic assignment. Some we could deal, what are the fundamentals we could deal with in details, and whereas some of the cases I had to live only with the basic concept, like mostly the dynamic traffic assignment model. But as I said, these are still evolving, and lot of things are there for you to know. So, if you are interested, do some self study and look at some of the research paper to learn more. So, with this I conclude. So, what we discussed here is the stochastic user equilibrium, the formulation and how to solve using stochastic equilibrium and then MSA to get the stochastic user equilibrium, and how this equilibrium is different from deterministic user equilibrium, and also gave you a little bit introduction to time dynamics. We said why we need it and what is the basic thing new is the introduction of this time dimension in the whole work. Thank you so much.